Hello and welcome, everyone. My name is Sergey Sokolenko. I'm a product manager at Amazon RDS. Today, I have with me Jeremiah Wilton, who is a principal engineer at Amazon Web Services. And we're going to be talking to you about Oracle on AWS and Amazon RDS. So in this session, I would like to spend a little bit of time talking about building secure database environments for Oracle. Then we're going to talk about migrating Oracle databases into AWS. We're also going to be talking about building fast and scalable workloads on Amazon RDS, as well as we're going to present a new project that Jeremiah has been working on building Oracle RAC clusters on AWS. So let's get started with secure database environments. First thing about security in AWS that you should know is about controlling access to your database. You should start with database access and privileges by creating a user that can only create, let's say, create and update tables, but not drop them or truncate them. You don't want to be in a situation where one of your users executes a truncate all and deletes substantial amounts of memory or storage in your database. The next level of security is network security. And you achieve that by defining security groups. You should have a security group for both your database as well as your application. And when you define the permissions for security groups, for your database security group, you should define the security group name of your application so that you don't have to use CIDRs and everything is transparent. Yet another level of security that AWS provides to you are VPCs, or virtual private clouds. Just a way for a customer to subdivide Amazon's web services environment into logically separate partitions. VPCs can be further subdivided into subnets. And you should have several of them. You should have a subnet for your database, a subnet for your application servers, and a subnet for your web servers. The subnets for your database and application servers should not be accessible to the internet because you don't want someone from outside to potentially compromise your data. Now, the subnet for your web servers should definitely be accessible through the internet if you are building a web application. Lastly, you control access by using what we call the Identity and Access Management, IAM. And you should definitely use this technology and the service to better control your users and permissions of your users. Beyond controlling access, there are many other things you can do to improve the security of your database. You can use encryption of data in transit to better protect your data in transit. You can also use auditing functionality available in Oracle to exactly know what's going on your database. But I would like to dive deep into one particular area which we improved quite a bit over the past year, which is encryption of data at rest. And we're going to start with a simple setup where you have an application accessing an Oracle database without any security. As some of you might know, Amazon RDS provides you with Oracle processes running on EC2 boxes accessing network-attached EBS storage. So in the simple setup that we are starting with, there's no encryption. You can get encryption easily by relying on a new technology we released this year, which is volume-based encryption of EBS. In this setup, the Oracle database doesn't even know there's encryption going on. So you can use your Standard Edition 1, Standard Edition, Oracle Enterprise Edition databases with this technology. You don't need to have TDE or Enterprise Edition to gain encryption. You have several options of how to manage keys with this technology. You can either use or choose to let Amazon RDS manage your master keys, master encryption keys, or you can choose to use the key management system, KMS for short, to manage and maintain your keys. And it's really simple to set up this encryption technology. When you create your database or when you modify your database, you select yes for enable encryption, and you choose which keys you want to use. Now, in addition to volume level encryption in EBS, you can definitely also use the TD encryption available with the Enterprise Edition Oracle. And again, you have two options here. You can either maintain or manage your own keys, or you can let Amazon RDS manage the keys for you. In this particular example, I'm starting with a setup where Amazon RDS is managing your keys. How do you set this up? In the database options, you choose the TD option. Some of you might be aware of the way we enable options in RDS, but for the rest, I'll just quickly remind. We have a concept called options. You can apply an option to a database, and the particular option you should be looking here for is called TD. If keys that are managed by Amazon RDS is not something you would like to consider, if you would like to manage your own keys, you have the option to integrate with a hardware security module service that we provide today. It's called Cloud HSM. With Cloud HSM, you are the owner and the manager of keys, and we provide the integration with the service. When you use TDE, the Oracle instance is definitely aware of the encryption that is going on, so the channel between your Oracle instances processes and the blocks in ABS is fully encrypted. In addition to improving our encryption story over the past year, we've also invested in making our workloads, Oracle workloads, HIPAA eligible. Some of you who are working in the healthcare industry are aware of the requirements that are imposed by the Health Insurance Portability and Accountability Act, or HIPAA for short. This legal framework imposes certain restrictions and requirements for managing patient healthcare information. So you'd be happy to know that you can now sign business associate agreements with AWS, and you can cover RDS for Oracle in such agreements. Those of you who already have BAAs with Amazon, you can grandfather the addition of RDS Oracle. You don't have to do anything extra. But even those of you who are not in the healthcare industry, you'll also be benefiting from the additional external third-party audits that we had to go through to get certified and to become eligible for being included in BAAs. So we get extensive audits by third parties of our operational and security processes, and every user of Amazon RDS for Oracle is benefiting from them. Now let's talk about migrating databases to RDS. We built our secure environments. Let's talk about how to move data into AWS. There are several reasons why you would want to move data. One is a one-time data migration when, for example, you're moving your workloads from on-premises to the cloud. Or perhaps you're starting with you already have a database in the cloud, but running on EC2, and you would like to move it to RDS. Once you have your databases in the cloud, you might choose to replicate them. You might want to continue replicating your on-premises database to the cloud, or you might want to choose to replicate back for disaster recovery purposes or for compliance purposes. Yet another good reason for having the ability to do ongoing replication is, for example, moving your transactional data from your transactional databases into BI systems, data warehouses. Redshift comes to mind as a good source, or sorry, as a good target for such a replication. And last but not least, you might want to choose to do ongoing replication if you want to offload some of the queries on your primary database and would like to do read replicas. How do we do data migration? There are a couple of methods. One is doing data migration in bulk, and the other one has the same name as one of the use cases, doing ongoing replication. We have recently introduced the AWS Database Migration Service. We launched on Wednesday. launched in preview. And I'm going to talk about it a little bit more. But there are also other methods of moving data. So for bulk loads, you can choose the standard Oracle tools: import, export, data pump, SQL loader, materialized views. You can also do create table as and inserts over database links. For ongoing replication, you also have options, including data pump and materialized views, as well as Golden Gate. Amazon RDS for Oracle supports Golden Gate as source and target. But we definitely want you to consider signing up for the Database Migration Service, because in addition to working in Oracle, Jeremiah and I are also working on the Database Migration Service, so we think it's a great tool. It simplifies a lot of the manual tasks you have to do with the other tools. I'm going to be talking about an example of what we recommended in the past for a high-speed database migration into the cloud before we release the Database Migration Service. And the reason I want to mention it is because it highlights some of the features of Amazon RDS that you should be aware and should be still applicable even after you start using other tools. So in my example here, I'm going to start with a 500 gigabyte database that I would like to move from on-premises to Amazon, to a RDS Oracle instance. I'm going to be using data pump for extracting my data from the on-premises instance. And I'm also going to be using a supplementary helper Linux host with multiple disks attached to it so that I can parallelize my I/O. The particular command I'm going to be using, you're seeing it right now on the screen. I'm doing parallel export, and I'm using compression. And this method allows me to compact my 500 gigabyte database in about 200 gigabytes. And it takes me about 2.5 hours to do the export because I'm using parallel I/O and writing to multiple disks on the Linux host. Now, after I got my multiple data files extracted, and by the way, so this method that you saw right now will generate about 18 files written to the three disks. I can now start moving this data to Amazon. And I'll be using a helper EC2 instance, again with multiple disks attached to it, so that I can parallelize the writing process as well. We have a recommendation for using a UDP-based transfer method. It works a little bit faster. And in this example, I was using Tsunami, which is an open source project that is optimizing the data transfer rates and using UDP for transferring files. So this process will probably take you about 2.5 hours. Once I have my data in my helper EC2 instance, I can now start moving it into my Oracle RDS instance. And I'm going to move it first to the data pump directory. Amazon RDS for Oracle allows you to move files into data pump. Generally speaking, we manage the instance for you, so you cannot really access data files on our hosts. But this is one of the directories you can access and can write because we would like you to be using data pump, or being able to use data pump, and importing or exporting files from Amazon RDS. The process of moving from my EC2 helper instance to RDS will take about 3.5 hours. And lastly, I need to ingest the files into my tables. So I'm going to be using this command. It's a bit long, but it does the trick. It uses the DBMS data pump package to import the files into my tables. And that step takes about 4 hours. However, because I'm parallelizing everything and not waiting until my data pump exports the files initially, I'm not waiting until I got all the files on the disks to transfer them. So I'm doing everything in a quick succession. The entire process can be done within about 7 hours. I mentioned this process because it's useful, and you should still be aware of it. But fortunately, with the database migration service, you don't have to do these steps anymore. You can get to your first migration task in less than 10 minutes now. You can set up a replication instance, you can set up your connections to sources and targets, and you can start replicating within 10 minutes. It's good to know that you can move data into data pump, through data pump, but this service is simple enough for not needing to know all these steps. The other cool feature about the database migration service is that you can keep your applications operational during the database migration process. In my previous example, I had a downtime of about 7 hours because my files were exported, so I couldn't take any transactions on my source anymore. With the database migration service, not anymore. You can keep transactions running on the source database, and you can switch your applications whenever you are ready. In addition to migrating data, the database migration service also allows you to do replication, either within RDS or within AWS. If you have multiple copies of the same database you would like to maintain, this service will allow you to do it. But you can also replicate into AWS as well as out of AWS. You can, for example, establish a disaster recovery solution, or this tool will help you building a disaster recovery solution, or perhaps integrating your data from the cloud into your on-premises systems that still need to be operational over the next years. Another cool feature of the database migration service is that it allows you to move data heterogeneously. So you don't always have to stay with the same engine you're starting. If you have a transactional load, for example, in Oracle, but would like to use a Postgres engine for reporting, you can use the database migration service to set up replication heterogeneously, and will move the data from your Oracle database to your Postgres target. If you'd like to sign up for the database migration service, please go to aws.amazon.com/DMS and sign up for the preview. I want to spend a little bit of time talking about the minimization of downtime that the database migration service allows you to accomplish. I'm going to start with a setup where my applications are accessing my source database on premises. And the first step I'm going to do is I'm going to create a replication instance in Amazon using the AWS Database Migration Service. So this instance is going to start pumping data after I connect to my source and target database, obviously, and select the tables and databases I would like to migrate. The database migration service will do a bulk load and will start replicating all the changes on your source until the target gets to a point, to its synchronization point, where it's pretty much the same as the source database. Once you see the transaction queue or the queue of changes that need to be replicated getting to 0, this is a good time point to switch your applications from your source database to your target database and completely migrate your system this way. I also wanted to share a few best practices for the database migration service in conjunction with operating Oracle databases. The database migration service is great for moving data, and it also provides a basic capability to migrate your schema, but it will only copy the tables and the primary keys from your source database to your target database. DMS does not yet support moving secondary objects, secondary indices, or stored procedures or triggers. So for the secondary objects, what you want to do is to use either the native Oracle DBMS metadata package, just to get the DDL of your source database, or you should use some of the other tools available with Oracle, such as SQL Developer. Just make sure that when you export the schema, don't export the data, because DMS will help you with that. Another recommendation I can share with you today is to optimize the performance of the migration task. You want to consider dividing your DDL into two parts. The first one is the tables and primary keys. This is really just the required objects that are required to accept the data from the source database without imposing any burden due to triggers or secondary indexes. The second set of scripts should include the remainder of your schema. And you should apply the second script when you have transferred the data and are ready now to build secondary indices and enable triggers and store procedures. To optimize performance of the database migration process, you should use our bigger C4 instance types. The Database Migration Service comes in two flavors, supporting two instance types, T2 for burstable loads, as well as C4 for high-performance data transfer. So definitely feel free to use the larger instance types if you would like to minimize downtime, if that is your objective. And another thing you should be watching out for is network, because in many cases, network will be the bottleneck when you move data from on-premises to the cloud. So what you want to do is you want to either sign up for a direct connect connection or use the larger C4 instance types because they have a bigger network interface and allow more bandwidth. I also want to talk about building and improving the performance of your workloads on Amazon RDS. And in this presentation, I'm going to use an example of a workload that has a mix of reads and writes. And I'm going to use this example to demonstrate some of the concepts I'm going to be talking about. So many customers, when they start analyzing and improving performance of their instances, they start with metrics. You can use the metrics available to you through the RDS dashboard. But you can also use the metrics available to you through CloudWatch or Oracle Enterprise Manager. Amazon RDS integrates with or supports Oracle Enterprise Manager, so you can use that tool to manage or to review your metrics and analyze the performance. In my particular workload, I'm doing a very long loop of inserts into an invoicing table. So every other time I do an insert, and every other time I do a select, a quick select, and a delete. So the ratio of writes to reads here is about 2 to 1. And I'm executing this workload on two connections to kind of demonstrate the what happens when you run multiple heavy-hitting connections. My instance is a M3 large instance. It has 2 virtual CPUs and about 8 gigabytes of memory. And I have allocated about 400 gigabytes of space for storage. So the first thing I'm going to do when I want to improve the performance of my workload as well as my instance, I'm going to look at the CPU statistics. And as you can see, CPU is being hit pretty heavily here. The average consumption of CPU is about 80 to 85%. I'm also going to look at my reads and writes. As I said before, the ratio of my writes to my reads is about 2 to 1, and you can see it easily in the dashboard. I'm getting about 600 to 800 writes per second, and about 200 to 400 reads per second. Yet another statistic I want to look at is the amount of readable memory, but it doesn't seem to be a problem yet. I still have about 2 gigabytes of RAM available to me. Free storage doesn't seem to be an issue. I have quite a bit of it. And the number of database connections is predictably 2, because I'm running two of them in parallel right now. When you go about scaling your instance, you typically have 4 things to tweak. The first one is the compute capability of your instance. And it's typically measured by the number of vCPUs. The other component of your RDS instance is memory. Then you have network. And lastly, you have storage. We used to offer a variety of instance families in the past, starting with a T1, M1, M2, M3. And we have recently launched support for T2 and R3 instance types. T2 instance types are very cost-effective, general-purpose instance types that allow you to use burstable, that provide you with burstable capabilities. So if you're running a workload that is not consuming the CPU on a constant level of the duration of 24 hours a day, but just need to be able to spike maybe for a couple of hours a day, T2s are definitely the instance types you want to consider, because they're cheap and they give you credits you can use during these bursts. The R3 instance types are the high end of our current capabilities, and you can go up to 32 virtual CPUs and 244 gigabytes of RAM. 2 weeks ago, we launched support for the T2 large instance type. The T2 large is an interesting one because it has 2 vCPUs, but 8 gigabytes of RAM. So if you have a reporting workload, for example, that only is used maybe for a couple of hours a day, but needs access to a large amount of RAM, that would be the instance type to consider. It's very cheap, and it fits the profile of infrequent use during the day. You need access to a lot of RAM. In my previous example, when I started talking about the performance metrics, you saw that the CPU of my instance was spiking. So I realized this is a bottleneck in my current setup. So I decided to scale my instance to the larger instance. The next step up from my M3 large is the M3X large. So I decided to scale to that instance type. And during scaling, what I'm going to do is I'm actually going to use a multi-AZ configuration for my instance to minimize the downtime that I will realize through the scaling operation. Here's a log of all the events that are happening with my instance during the scaling process. It takes about 25 minutes to apply the scaling, to scale my instance from the large size to the X large size. But because it's a multi-AZ instance, my instance is only unavailable for about 2 minutes. Actually, less than 2 minutes, only 105 seconds. So I was able to continue taking transactions on my source database for the first 10 minutes of the scale operation and the last 10 minutes of the scale operation. Because what multi-AZ does, it starts preparing the secondary host, starts upgrading my secondary host, while I can still continue doing transactions on the primary host. And only when the secondary host is available does the multi-AZ technology switch and do a failover and provide me with replace the endpoints and give me a kind of access to my new primary, which was the old secondary. So what happened to my instance after scaling? CPU definitely went down. It's now about 50 to 55%. My reads and my writes increased. And if you look in detail on the detailed statistics, the duration of the previous run was about 36 minutes. After scaling, I was able to get it done within 23 minutes. My CPU was around 80% in the past. It became around 55% with the larger instance type. My writes increased by 20–25%. So it's definitely a CPU-bound workload, I didn't have any bottlenecks on writes. The reason why I got more writes done just because I'm doing it faster, and so there's more to be written to my disk. I did not see a 2x improvement in my writes, but it's most probably because I'm running 2 connections and they can generate this much load. My reads increased as well by another 35–40%. And if you want to see a quick comparison of all the important metrics, I was able to, by scaling my instance, by increasing the number of eCPUs, and by increasing the number of memory available to me, I was able to reduce the duration of my workload, decrease the consumption of CPU, increase my read and write rates. The last component that you can tweak in Amazon RDS is storage. And one of the improvements we've done over the past couple of months was extending the available, the maximum storage size available to you from 3 terabytes to 6 terabytes. I want to talk about the performance of storage and how to tweak it and what the different characteristics are a little bit. Some of you might know that with Amazon RDS, you don't get instant storage, but what you get is network-attached storage. There are 3 types of network-attached storage you can choose. You can start, or you can choose magnetic storage. Magnetic storage comes in varieties from 10 gigabytes to 3 terabytes, and you can get a performance of about 100 I/O operations per second, burstable to maybe several hundred I/O operations per second. Now, the next storage type you can choose is GP2, or general purpose storage, using SSD. And you can go from 10 gigabytes to 6 terabytes. You get 3 I/O operations per gigabyte that you reserve. And this capacity can actually burst up to 3,000 I/O operations per volume. We do recommend allocating at least 100 gigabytes because with GP2, if you allocate smaller amounts of storage, you might get lower performance than your magnetic storage because of the 3 I/O credits per gigabyte that you receive. Some of you might know this, but I'm gonna mention this as well. If you create GP2 volumes that are larger than 3 terabytes in size, you actually get a baseline performance, not burstable, but baseline performance of 10,000 IOPS. And so GP2 is definitely becoming a good alternative to using the next storage type that I'll be talking about, which is provisioned IOPS. Provisioned IOPS are our high-end storage type, and it comes in varieties from 100 gigabytes to 6 terabyte, and you can allocate up to 10 I/O operations per gigabyte reserved, and your performance of the storage volume can go up to 30,000 provisioned IOPS. What are the best practices for using or improving storage performance on Amazon RDS? The first one is realizing that you have up to 1,000 megabits per second on each of the channels, reads and writes. This is the maximum performance of Amazon RDS storage. So you get up to 105 megabits per second each direction, or total I/O performance of 210 megabits per second. The 210 applies if you have a perfectly balanced 50-50 read-write workload. How many of you know what a first touch penalty is in ABS? See, a couple of hands. So first touch penalty means when you restore a snapshot or when you create a new instance, the first operation on the storage volume in Amazon RDS as well as on ABS will be somewhat slower than subsequent operations with that block, storage block. There are a couple of techniques you can use to even out the performance of access. For example, you can do just read all these blocks in one big select statement after initialization of your instance. And this way, you even out the performance. It's just a performance optimization technique. You don't have to do it. Eventually, after a couple of minutes, the performance of your storage access will equalize. But if you would like to have a consistent performance, then this is something you might want to consider. And lastly, when you use GP2, it's a great storage type, and you saw that you can realize great performance with it, especially on larger volumes. On smaller volumes, be aware of the 3 I/O credits per gigabyte that you get. So if you reserve less than 30 gigabytes for your GP2 database, you will actually get lower performance than magnetic storage. So you might want to consider using magnetic storage for your smaller databases and using GP2 for somewhat larger databases. So far we've talked about security and scalability and performance improvements in Amazon RDS. We also have lots of customers who would like to run Oracle workloads on EC2, especially when they are rack-based workloads. And I would like to invite Jeremiah to talk about his project on building Oracle RAC on AWS.
Thanks, Sergey. Who would like to run RAC on EC2? Not that many hands. OK, well, I'm going to tell you how anyway. Sorry, my voice is just going to come back after half an hour on that chair. So we believe that we do have some significant number of customers that would like to be able to run RAC on EC2. And for a very long time, people have said, well, it's not possible. But we started looking at all the different reasons that our customers would want to be able to do that. One really simple reason is that a lot of customers would just like to be able to build out their non-prod environments on EC2. Maybe keep their on-premises rack or traditionally hosted rack clusters for production, in a traditional hosting environment on traditional hardware. But for developers, it's very expensive to have a rack cluster for every developer. That's not economical. So that's one really good use case. One good reason that you would want developers to have access to RAC is if they're developing software against Oracle that's ultimately going to run in production Oracle RAC. They want to be able to tell if they're introducing workloads that are going to that are going to be affected by RAC-related regression cases, such as if they were going to cause latency in the application as a result of forcing RAC to share blocks across the interconnect, or if they were going to affect the availability because maybe their application doesn't know how to use application failover or FAN or one of those kinds of things. So those are kind of reasons why you'd want developers developing against RAC if they're going to produce software for RAC. Another good thing that we noticed is that one of the big selling points of RAC is that you can start with just a couple instances, but then, should you need more capacity, you can add more instances to the cluster, assuming you have a workload for which that is an effective scaling technique. And that is very, very close to what we say about EC2. If you need additional capacity, add more instances. RAC is actually a very good match for our elastic scaling characteristics. Then there's also the question of peace of mind. There are some customers who look at our largest instances, which are pretty beefy on EC2, and say, well, this will do for now with single instance Oracle, but what if our workload exceeds the largest instance that you guys provide? We've got nowhere to go. If we were on traditionally hosted hardware, we could go buy a gigantic engineered system and pay a bunch of money for that, but at least we'd be able to scale beyond the size of that machine. If we can run rack on EC2, it would be pretty great because you could, if you exhausted the capacity of our largest instance, you could go ahead and add another one, add one after that. So just expand beyond that size. Another reason customers like to use rack in general is to provide like high availability at the instance and app level. And that's something that you would have to engineer around if you were doing this yourself on EC2. And even on RDS, we do have multi-AZ availability feature. But the failover time is slightly longer than the failover time would be for rack if you had everything implemented correctly at the application to take advantage of rack failover. So some customers are looking for that application continuity capability in Oracle, near zero downtime. And if you're, from a instance and host level perspective, rack provides you with that availability solution. Another question a lot of our customers have is when they're going to reach a point of diminishing returns on their instance count. Even if they're hosting their rack cluster in traditionally hosted environment, maybe they've gone up to like 4 or 5 or 6 nodes, and their scaling plan is should they exhaust the capacity of 6 nodes, they're going to add a 7th, 8th, 9th, 10th, all the way up to a 64th. The question is going to be, at what point are they going to saturate the interconnect? At what point is adding nodes to the rack cluster going to stop scaling their workload and going to start causing it to scale inversely, which will happen at some point in most workloads. If you could create lots and lots of nodes of rack and point your workload at it in a virtual environment, you could test this question without buying all that physical hardware to test it out and find out at what point, at what number of nodes, your workload begins to scale inversely. And so that's another great use case for running rack on EC2. And there are the applications, third-party apps that have a list of requirements, and some of them say they require rack. And whether or not you believe that's a good requirement for them to be putting out there, that requirement still seems to be in some third-party applications list of prerequisites. So we want to be able to provide what customers need to run their apps on AWS. Another use case is customers who want to get to AWS now, but don't want to re-engineer everything for like multi-AZ and RDS and all the other stuff. They just say, like, look, we're buying into the cloud idea, but we just want to lift and shift into EC2 now and start taking advantage of the cloud-native capabilities gradually over time once we're in. And being able to deploy rack in EC2 allows them to lift and shift their existing design architecture using rack from on-premises into EC2. And finally, customers want it, and we are interested in doing what our customers want. And so we have started thinking about this. Now, historically, we have said that rack isn't supported on EC2. And there are a few reasons that was a message that we had. As you know, we store data, generally persistent data, on EBS in EC2, the elastic block store. And as you probably know, EBS volumes can only be connected to one EC2 instance at a time. They can't be connected to multiple EC2 instances at a time. So they can't serve that shared storage requirement that rack has. So we started thinking about a good way to do this. And we thought that it would be kind of interesting if instead of serving the storage from EBS, we built our own ISCSI NAS device out of an EC2 instance and served storage from there. This allowed us to, and we tried this out and it worked, this allowed us to take that EBS volume and share its storage across multiple nodes using ISCSI. Now, some of you might be looking at this and already calculating what the I/O latencies are going to be like in your heads. Does this pass the I/O latency sniff test? No, it does not. Right? One I/O from the rack node down to the ISCSI target, one down to the EBS volume. EBS volume answers back. Finally, the ISCSI target can answer that I/O request back. unless we have got the stars aligning perfectly, it's not a production class I/O scenario. It might be valid for test and dev though, or non-prod or low I/O requirement applications. So don't rule this completely out. But we said, look, this is not going to serve the highest end customers that we want to serve. So we tried to think of something else to do. So back to the drawing board on the ISCSI target there that we were building for serving storage. Well, if you look at what instance classes we provide, we actually provide some really interesting high-end instance classes in EC2. And one of them is the i28XL. And the i28XL has onboard SSD, quite a bit of it, like 5 or 6 terabytes. And so we thought, wouldn't it be interesting if we, instead of serving EBS, serve the onboard ephemeral SSD from the i28XL instance just as a standalone storage node. And this passes the I/O performance sniff test, but there's another sniff test it doesn't pass, which is the durability and redundancy sniff test. There's only one of these, and it's ephemeral storage. What if somebody terminates it? Your data is gone. What if it just fails for whatever reason? It could happen. Probably wouldn't, but it could. Your data would be gone. So that's not acceptable. Fortunately, we have ASM. And ASM has normal redundancy capability and can mirror your data in between multiple volume locations. And so by creating 2 of these, we can use ASM's normal redundancy, or even high redundancy, if we wanted to create 3 of them, to create a highly redundant storage service for rack in EC2. And it turns out this works pretty well. You can kill one of these, and everything just keeps on running. Bring it back up, and you can put it into, you can have it begin resyncing, and you can, of course, choose the speed with which you have it do that. So this is the storage design we came up with. We used OpenISCSI 2.0 for all this. OK, there's another reason that people have long said that you can't do rack on EC2, and that is the lack of multicast network support. Within VPC, rack requires multicast. It doesn't require it all the time, by the way. Rack only uses multicast when it's doing cluster configuration and reconfiguration. So like if a node drops and the cluster has to reconfigure, or when you're creating the whole thing to begin with, it has to be able to do multicast communication. So we needed some kind of solution to provide customers with multicast capability within the VPC network that they would be using. We actually looked around and found an interesting solution. We used a product called N2N from NTOP, which is a point-to-point VPN solution, to create an overlay interconnect on top of the 10 gigabit Ethernet network that's available within your VPC for cluster compute instances. This is a really versatile point-to-point VPN, and it's super easy to set up. It creates a community of nodes within the VPN that can communicate with each other using multicast and normal IP. And the whole thing is coordinated by a single node, which we actually installed on the storage server, so that the storage server acts both as ISCSI server and also as the N2N coordinator node. So that's how we did the interconnect. We used N2N from NTOP. All right, let me tell you a little bit more about how we built this thing out. First of all, I'm happy to announce that we have built a prototype, and we're making that prototype available to our customers at this URL at aws.amazon.com/articles. You'll find a tutorial there that will walk you through the setup of this reference architecture that I'm going to tell you about. In addition, we've provided 2 marketplace AMIs that you can get from the AWS Marketplace, and that tutorial gives you links directly to that. And one of those AMIs is for the storage server, and the other AMI is for the rack nodes. And you can use this to create as many, as large of a rack cluster as you like. And this design, by the way, that I'm about to show you is meant to provide you with a toehold. It's not meant to be your ultimate design. It's meant to show you that you can create what ultimately is a scalable production class architecture for RAC on EC2. And from this point, we expect you to also innovate, right? Innovate for your own workloads, innovate for your own architectures, designs, and requirements. So this shouldn't be your endpoint. This should be your toehold to getting going with RAC successfully on EC2. Started with a VPC. This is something we recommend you only run within a VPC for a lot of reasons. VPCs have many more networking features than you can get in EC2 Classic. All kinds of great networking features in there. We also use Route 53. Route 53 is our DNS service available in AWS, and we use that for all the stuff that you would need DNS for a RAC cluster, the scan addresses, the VIP names, and all that kind of stuff that you have to set up successfully and have working in order to have a working RAC cluster. And we use this in the form of a private hosted zone. Turns out you can use Route 53 to do DNS for like public DNS, but if you do it within VPC, you can set it up as a private hosted zone so that you so that the DNS resolution is restricted to just within your VPC. We did the whole thing within a single subnet. It seems like the best thing to do to keep latencies low and keep everything neat and clean and easy to do. We also used a feature of EC2 called placement groups, which allows you when you're using, when you bring up instances, for those instances to be located nearby to each other from a network topology perspective within the EC2 network, so that you have minimized latencies in between components. So this is exactly what we want. We want minimum latencies in between the RAC nodes and the storage node components. We also use dedicated instances, so we could get the entire capacity of the box when we ran these things. Started out by building our ISCSI target, just like I was telling you about on the i28XL, with its 6,400 gig of ephemeral storage. We striped that and made it available to the operating system using LVM, chopped it up into a chunk for a data volume for ASM at a recovery area volume, and left about 800 gig free. We served all this up using ISCSI target software, Target D, the daemon software for ISCSI. Then we created a second one for redundancy, as we talked about before. Next, we built out our RAC nodes on C3 8XL classed instances. These are pretty beefy compute-oriented instances. In our first run at this, we did 2 nodes. By the way, it happens that there's more ephemeral SSD available on the RAC node as well, and I'll tell you what we use that for in a minute. So we presented this storage up to the RAC nodes using ISCSI initiator software on the RAC nodes, which allows that to appear as devices, that storage to appear as devices on the RAC nodes. And we set up our virtual interconnect over the 10 gigabit Ethernet that's available within your VPC. We set up ASM and grid infrastructure so that the cluster was formed. And we were able to present all that storage from the storage servers up via ASM as disk groups. We used normal redundancy so that we would be protected from loss of one of the storage nodes. Then we built out the database software using database 12c. And this all works, and it works pretty well. As sort of like the coup de grace, we decided to use that 640 gig of ephemeral SSD that comes with the C3 8XL as flash cache, because we built this out on OEL 7, which allows us to use flash cache, which further improves the performance of this reference architecture. So we can look at that again for a minute if you want. And this is also a diagram which is available on that article. So you can sort of feast your eyes on that there. I know it looks complex, but the cool thing about it is the AMIs that I've given you in the marketplace are pretty much completely set up to do this. There's very little configuration and setup required by you when you deploy this. It's basically the storage nodes will come up, the RAC nodes will come up, all the storage will already be there. You have to download your own software, right? Because we're not Oracle software distributors. So you go and log into eDelivery yourself to get the database and cluster software. And then once you've got that downloaded, we've got response files that set up everything else for you. So it's pretty turnkey. So we'll go over a little bit what we've talked about today, and then we'll have a couple minutes for questions. We talked about securing database environments on AWS and RDS. Talked about migration and our new migration service, the Database Migration Service. We talked about scalability on RDS and performance optimization. And we talked about the fact that you now can build rack clusters on EC2 should you want to. That's about it. Thank you very much. Please return evaluations or evaluate us on your mobile app. And we're ready for questions if you have any.